Hello and welcome. And we're going to talk about today is how to create a differential equation. How to create a differential equation. And the key thing when you're creating differential equations is, especially in AP calculus, is that you have this little saying. All right, some sort of rate is directly proportional to blah. Okay. The thing is that when you have a differential equation, we're talking about rates. And so when you say a rate is directly proportional, what that is saying is that you're taking a value and it's going to be taken. So whatever this parentheses is, and maybe I can put that just a parentheses there so you just know a placeholder for that. And so we're doing this parentheses, and usually the rate is with respect to time, just like a kind of related rate, which is directly proportional, is meaning equals. Now, directly proportional means that we are going to be taking that to similar values. So directly proportional means we have a constant proportionality k, all right, times whatever value they have over here. All right, so we'll call this A. We'll put A right there, and we'll have whatever this is to B. Okay, to B or not to B, that's a question. So we just plug in those values in there, and so we have directly proportional. We create this differential equation. Now, there's a bunch of different differential equations that are in applications for real life, and a lot of them have to do with exponential and growth and decay models. And here is an example of that. So here we go. It says a new theme restaurant in town is being tested for health department for cleanliness. Health inspectors test the kitchens, floors, and determine that the rate of bacterial growth is proportional. So let's just stop right there. So the rate of bacterial growth. So we're going to write that out. Now let's say that is dB. All right, B is our bacteria. So I'm just going to write that here. B equals bacteria. All right, so that's our bacteria. And we'll say that is, all right, proportional. Now it says directly proportional. Proportional means we're going to have this constant K, all right, to what? To the number of bacterial colonies. So in this case, it's actually proportional to B, the number of bacterial colonies we have there. Okay, so the rate of change of B is directly proportional to the bacterial colonies themselves. Now, what is this right here? What do we have when we create something like this? Well, this is a very, very common differential equation, all right? Many times you see it written as this, dp dt, all right, equals kp, all right? Sometimes you have it like that. Sometimes you have an a there. But this is a very, very common basic differential equation. And what we're going to do next is we're going to solve this differential equation because we're going to answer this question. And it's going to say this. So we're going to find out some more information here. So they plant 10 colonies. All right. So this right here is going to tell us our points from our solution curve. So when t equals 0, our bacteria equals 10. All right, 10. And then we know that 15 minutes later, so when t, all right, when t equals 15, when we return, their colonies have risen to 35. All right, 35 bacterial colonies, and we have that right there. Okay. So we're trying to figure out how many colonies will there be 1 full hour after they've planted the original 10. All right, so we're trying to figure out what is, all right, B, question mark, when we have T equaling 1 hour. So that's going to be 60 minutes, and each one of these in minutes. Okay, so 15 minutes, these are the colonies. All right, and we have started off with that many colonies and so on and so forth. We're trying to figure out what that is, the colonies, all right, after 60 minutes. All right, so without further ado, let's solve this problem. So let's find out what happens when we solve this differential equation. So making the differential equation is actually pretty easy. We just look for these keywords when we're writing it. Now, just like this, whenever we solve a differential equation, we first want to separate variables. So we're going to do dB over B, and we're going to keep the K over here with the dt. Okay, so that's our separation of variables. We're going to integrate this now, both sides. This side, well, since we're integrating with respect to B, we have 1 over B, which is going to be natural log of B, and that's going to equal the integral of K. K is a constant, all right, that's a constant of proportionality, and that's going to be T, all right, and then don't forget your C, all right, your C. All right, so there is our differential equation. From here, we want to now figure out solve for C. So I'm going to take this initial condition. This is what we call the initial condition. All right, and we're going to plug that point in there. So I'm going to plug in 0 in for T. So we have K times 0. All right, and we're going to have natural log of 10, and that's going to be plus c. So c is going to equal the natural log of 10. Awesome sauce. So this is what we got next. Going from here, oopsies. Let me get rid of that. I apologize. All right, so continuing on our mathematical journey, we have now the natural log of b, okay, equals kt plus the natural log of 10. So now from here, we're going to solve for b. All right, solve for b. So we're going to get rid of natural log. We're going to both sides. When we do that, we have b equals e to the kt plus natural log of 10. Well, that simplifies, my friends, to e to the kt, using a little bit properties of logs and exponents. All right, right here, these are inverse of each other. They cancel out. And we're left with is 10 e to the kt power, and that equals b. Oh, now this is where I'm going to just pause a second. Is that right here, if you're in pre-calculus class, all right, this should be very, very familiar to you. This is actually what we call an exponential model. Okay, exponential model. You might recall like the PERT formula when you did rates of change for continuous growth. A lot of times maybe you'll see this where it's a of t equals our initial condition a sub 0 times e to the kt power. That is a basic exponential growth formula where this is your initial condition. Okay, and k is our rate of change, our basic rate of change. All right, so now we can see that this, all the way up here, this formula, this basic formula, this differential equation, dB dt equals kb, all right, or any one form of that, when you notice that the rate is directly proportional to, all right, the amount itself, that is an exponential growth model, all right, awesome. And so now from here, whenever we see that, we can kind of simplify it that way every single time. And we're going to go through another problem in just a little bit. Well, let's solve this rest of the problem. So we have this now, just like this. Now it's becomes a pre-calculus problem. So in order to solve this for t, we have to figure out what k is. So we need another point. So we use our initial condition first, and then we use our second point here second. So I'm going to use this one. I'm going to plug in 15 and 4t. So I have k times 15. All right. I have E, I have times 10, and we have 35 bacterias right there. We'll solve for that. We have 3.5, all right, equals E to the 15K. Well, natural log of 3.5, all right, and that's going to equal 15K when we're doing algebra. And so finally, we have this K is going to equal the natural log of 3.5 divided by 15. Boom, nailed it. All right, so we can put this in our calculator, maybe round to 4 decimal places. That would probably be good. Or you can just leave it like that, and that would be your answer. So like I said, this is what we have for, maybe you've done this in your pre-calculus classes, maybe advanced algebra or algebra 2 classes. So right here, this is approximately, all right, 0.0835. I'm going to round to 4 decimal places just to be on the safe side. So right there, I use this point, plugged it in to solve for k. So now we're going to go one step farther. We're going to simplify this. So what we have is b of t, that's our function, 10 e to the 0.0835 t. And now we're going to solve for our final answer. What is the value of b when t equals 60? Well, we're going to plug 60 in there. And so what we have is, what is b of 60? 60 minutes or 1 hour. We have e 0.0835 times 60. Put into thy calculator. And what we have then, hopefully I will do all this correctly, 0.0835 times 60. That's what I'm doing right here. You probably can't see me. And we have this. Wow, that is a lot of bacteria. And so we have about 14,000, or sorry, 1,499. All right, 0.047. All right, bacteria colonies. Boom, boom. And that's what we have. All right, awesome. So just to kind of review, when you are finding differential equations, you're looking for rates. And what they will say is that they'll be given a rate that is directly proportional to another value. Generally, this can be equal. When they are equal, like this one, we know this is going to be an exponential model, either growth or decay. In this case, this is a growth model because the k was positive. All right, well, I hope this helps you out. Good luck and God bless in the rest of your problems.